Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be drifting into one of the quietest and strangest places in the universe. A region where space bends, time slows, and much of what we know about reality begins to dissolve. We're going to explore the mystery of black holes. Not just what they are, but what they might contain. Not just how they bend light, but how they bend the very rules of the universe. What lies beyond their edge? Is there even a surface at all? And if something falls in, does it vanish forever? Out among the stars, black holes wait in stillness. They do not shine. They do not speak. And yet they shape entire galaxies. They bend the sky and capture time itself. So tonight, we begin with a question. What if gravity isn't a force at all, but something deeper, stranger, and more fundamental? Before we can understand black holes, we need to understand gravity, not as a force, but as a shape. This may sound strange, but this idea was one of the great shifts in physics during the early 20th century. It began with Albert Einstein's insight that space and time are not separate things, but part of a unified fabric, a fabric that can bend. In Einstein's theory of general relativity, gravity is not a mysterious pull acting at a distance. It is what happens when mass causes space-time to curve. The motion of objects, then, is not guided by invisible forces, but by the shape of the space they move through. Imagine setting a marble on a stretched sheet. If the sheet is flat, the marble stays where you place it. But if you put a heavy object in the center, the sheet dips. The marble will roll inward, not because something is pulling it, but because the surface beneath it is now sloped. Gravity, in this view, is a response to curvature. Earth doesn't fall toward the sun because it's pulled. It follows the curve of space created by the sun's mass. This same idea applies everywhere, on planets, around stars, and in the most extreme case, at the heart of a black hole. When too much mass is squeezed into too small a space, space-time doesn't just curve gently, it folds in on itself. At a certain threshold, the curvature becomes so steep that no path leads back out. Not even light can escape. This is what defines a black hole. But it is not a hole in the sense of an empty place. It is a region of space, real, physical, and structured, in which the shape of space-time leads only inward. A black hole is not an absence. It is a presence, dense, curved, and invisible. The boundary of this region is called the event horizon. It is not a surface in the usual sense. You cannot touch it or bounce off it. It's not made of matter. It has no texture or temperature. But it marks a profound division in the universe. From outside, signals can still escape. From inside, they cannot. The event horizon is where the paths of light and everything else turn inward forever. It is the edge of visibility, the point of no return. If you were floating just above the event horizon, you could still send out a message. Light from your ship would still reach distant stars. But step 1 inch farther, and all paths forward would lead deeper in. There is no outward direction anymore. Not because something blocks you, but because the shape of space itself no longer includes an escape. The event horizon is the point where geometry overrules intention, where direction stops being a matter of choice. This boundary, strange as it sounds, is smooth. If you were to fall toward it, you would not feel it pass. There is no jolt, no flash of light. The curvature is strong but not abrupt. For many black holes, especially the supermassive kind, the experience at the horizon might be almost gentle. From the outside, It appears as an invisible shell, but from within, it is a silence that deepens, a future that narrows to a single destination. The event horizon does not destroy you. It simply removes you from the story the rest of the universe can tell. So what happens when something falls in? From far away, it looks like time itself begins to slow. A spaceship drifting toward the event horizon appears to move more and more slowly as it nears the edge. Its light stretches out, redshifting into invisibility. To a distant observer, the ship never quite crosses the line. It simply fades. But from the ship's own point of view, the experience is very different. Time moves normally. Instruments tick. Clocks count. The boundary is crossed in a moment. And once crossed, the fall continues, quietly, unstoppably. Inside the horizon, there is no turning back. The future, as defined by the structure of spacetime, leads only deeper in. The ship, or the star, or the signal, whatever it may be, descends further into the curved interior. But it doesn't fall toward a center in the way we usually imagine. It falls toward a different kind of end. A place not marked by distance, but by the breakdown of the rules themselves. This is what we call the singularity. And though the word is familiar, its meaning is something stranger than we often assume. The singularity is not a thing. It is not a point in space. It is a failure of the map, a place where the equations of general relativity stop working. According to the math, the density of matter becomes infinite, and the curvature of space-time becomes unbounded. The paths of light and matter end, not because they hit something, but because they have nowhere left to go. Time itself seems to stop making sense. And yet, this is not a physical object. It is the edge of our understanding, a region where the known laws of physics no longer apply. Some physicists believe the singularity is real, that space and time truly end at a final point. Others think it's a placeholder, a sign that our theory is incomplete and that a deeper framework, perhaps one that includes quantum mechanics, must take over. Until we have such a theory, the singularity remains a mystery, a place predicted by mathematics, but invisible to all observation. Hidden always behind the horizon, it shapes the black hole from within, while remaining forever beyond our reach. The singularity sits at the heart of classical black holes, but it is not part of the observable universe. No light escapes it. No signal arrives from it. We know it only through the behavior of the space around it, the way orbits twist, the way time stretches, the way matter vanishes from view. The singularity is not the thing we see. It is the reason we see nothing at all. Its presence warps the rules, curving every path inward, until escape becomes not difficult, but impossible. In this sense, a black hole is not a hole at all. It is a space, wrapped in a silence so complete that the universe cannot see inside. What enters does not come back. What lies within cannot emerge. And yet, it is not destruction in the usual sense. The mass is still there. The influence remains. Gravity still acts on the world outside. The black hole holds what it swallows, even if it cannot return it. It becomes a kind of memory, sealed behind a boundary that nothing can cross in reverse. From far away, a black hole does not look unusual. It has no visible features, no glow, no outline. But its gravity reaches out just like any other massive object. Planets could orbit it. Light could bend around it. If you didn't know what lay at the center, you might think it was just a particularly heavy star. This is one of the most surprising things about black holes. From a distance, they behave almost normally. The strange effects only appear when you get close. when the curve in space begins to steepen. Imagine replacing the Sun with a black hole of the same mass. Earth would continue to orbit, just as before. The light would vanish, but the pull of gravity would be unchanged. This tells us something important. A black hole is not special because it pulls more strongly. It is special because it compacts that pull into a smaller space. The curvature of spacetime becomes extreme, only near the horizon. Farther out, the geometry softens, and the rules of motion return to something familiar. What makes a black hole unique is not the force of gravity itself, but the structure it creates. It is a region of space where the normal paths, the geodesics, curve inward forever, where time tilts toward a single outcome. The black hole doesn't pull things in like a vacuum. It simply offers no route out. It warps the map in such a way that all roads lead down. And once you're inside, those roads are all there is. The direction of outward ceases to exist. One common image is that of a black sphere or dark pit. But these pictures are misleading. A black hole has no surface. It has no outer edge you could touch. The event horizon is not made of matter. It is a boundary defined by light and causality. If you were falling in, you wouldn't bump into anything at the edge. You would pass through, unaware of the transition. The horizon is not a wall. It is a moment, a change in the shape of time. In this way, a black hole is both real and intangible. It can collide with stars. It can grow by swallowing matter. It can orbit, merge, and radiate gravitational waves. And yet, it has no structure that can be touched. The place where it begins, the horizon, is not a location in space, but a feature of the space-time itself. The closer you look, the more abstract it becomes. Not a shell, not a crust, just a boundary where escape is no longer an option. Even though the horizon is invisible, it is precise. It has a measurable size called the Schwarzschild radius. This radius depends only on the mass of the black hole. For the Sun, it would be about 3 kilometers. For Earth, less than 2 centimeters. The more massive the object, the larger the radius. But the nature of the horizon remains the same. It is not a thing that blocks. It is a place beyond which all futures fall inward. Not a surface, but a silence. Inside the event horizon, space and time switch roles. What once was a direction becomes a kind of future. The inward fall is not just a choice. It is what time becomes. Every second carries you closer to the singularity, not because you are being pulled, but because all paths through space-time now point that way. Just as we cannot stop time from moving forward, an object inside a black hole cannot stop its descent. The geometry of the interior defines its own version of inevitability. This interior is not simply empty. It has structure, even if we can never see it directly. The curvature increases steadily. Tidal forces grow stronger. The separation between objects begins to stretch in one direction and squeeze in another. The farther you fall, the more extreme the environment becomes. But still, the experience is shaped by the same principle. Space-time is not flat. It is folded inward, and every path through it narrows toward the core. This is what a black hole truly is, not a hole in the universe, but a region where the shape of space curves entirely inward. It is defined not by what it is made of, but by how it bends what passes through. It is a place where motion becomes directionless, where time becomes location, and where gravity is no longer just a force, it is the shape of destiny itself. the outside sees darkness. The inside follows a map that leads to a place we cannot reach. The simplest kind of black hole is one that doesn't spin, doesn't charge, and doesn't change. It is perfectly spherical, static, and defined by only a single property, its mass. This type is called a Schwarzschild black hole, named after Carl Schwarzschild, who first solved Einstein's field equations for a non-rotating point mass. It is the cleanest, most symmetric version of a black hole, and it serves as the starting point for understanding all the rest. A Schwarzschild black hole has no hair, no extra features, no distinguishing traits. It looks the same from every angle. The space around it curves smoothly, and the event horizon forms a perfect sphere. The size of this horizon depends entirely on how much mass is contained inside. There is no surface beneath it, no structure suspended in space. The geometry itself defines the boundary. Mass determines radius. Radius defines the shape. And the shape sets the stage for everything else that follows. Despite its simplicity, this solution is profound. It shows that black holes are not exotic outliers, but natural outcomes of Einstein's theory. You do not need strange physics to make one. You just need enough mass in a small enough space. Compress Earth into a marble. Compress the sun into a city. The theory takes care of the rest. The result is not a weird object sitting inside space. It is space itself, rearranged into a region where time and motion curve inward with no return. In the real universe, most black holes are not perfectly still. They spin. And this rotation changes everything. A spinning black hole is described by the Kerr solution, found by Roy Kerr in the early 1960s. Like the Schwarzschild solution, it solves Einstein's equations exactly. But instead of a motionless sphere, it describes a whirling structure, where spacetime itself is dragged into motion. This frame of rotating geometry surrounds the black hole and alters the behavior of everything nearby. The faster the black hole spins, the more distorted this space becomes. The event horizon is no longer the only structure. Rotation introduces a second boundary, an outer region called the ergosphere. Here, the fabric of space is not just curved, but twisted. Any object within the ergosphere is forced to move. It cannot remain still, even in principle. Not because it is being pushed, but because the space around it is rotating. Even light must swirl with the flow. This strange effect is called frame dragging. It means that space-time itself is pulled around by the spinning mass. In ordinary physics, we think of space as passive, a backdrop. But in general relativity, space is active. It bends. It moves. Near a Kerr black hole, it rotates. An observer inside the ergosphere will find that every direction includes a component of spin. There is no stationary point. Everything is carried, quietly but firmly, around the axis of the black hole. The ergosphere lies just outside the event horizon. It touches it at the poles, but stretches farther out around the equator. Within this region, something remarkable becomes possible. A particle entering the ergosphere can split. One part falls in. The other escapes with more energy than it had before. This is called the Penrose process, named after Roger Penrose, who proposed it in the 1970s. It allows, in theory, for energy to be extracted from a black hole's rotation. This does not violate the rules. The energy gained comes from the spin itself. The black hole slows slightly, and the escaping particle carries away the difference. Over long periods, this process could allow a black hole to lose angular momentum, gradually shedding its rotation. While it is unlikely in natural settings, it reveals a deep truth about these objects. They are not perfectly isolated. Under the right conditions, they can give back. Not mass and not light, but spin. The ogosphere is not a place we can visit, but it is a region with measurable effects. Light from near its edge is twisted. Particles orbit differently. The structure of space-time itself becomes dynamic. In this way, a spinning black hole is not just a deeper version of a still one. It is something qualitatively new. A whirlpool in the fabric of the universe where gravity and motion blend into a geometry that is both elegant and strange. The Penrose process is more than a mathematical curiosity. It reveals something subtle about the relationship between motion and energy in curved spacetime. When a particle enters the odosphere, its trajectory bends with the flow. If it splits into two, one fragment can be sent deeper into the black hole, while the other escapes. The trick is in the conservation of momentum. The fragment that falls in can carry negative energy, as seen from far away, allowing the other to escape with more than it started with. This is not free energy. It comes from the rotational energy of the black hole itself. Over time, repeated interactions like this would gradually slow the spin. The total mass of the black hole would remain, but its angular momentum would decrease. The process is inefficient in most astrophysical settings, but it is theoretically sound. It shows that even something as closed off as a black hole can interact with the outside world, not by letting things out, but by allowing its properties to change. The concept was later expanded by Stephen Hawking and others into the idea of black hole thermodynamics. A spinning black hole has more than mass. It has angular momentum, surface area, and entropy. These quantities obey rules that look very much like the laws of thermodynamics. The Penrose process, in this context, becomes a form of energy transformation. It doesn't violate any principles. Instead, it reveals that black holes may be subject to deep and universal laws, laws that govern not just matter, but the very structure of space. Deeper inside a Kerr black hole, the geometry becomes stranger still. Unlike a non-spinning black hole, which ends in a single point, the Kerr solution predicts something more complex. The singularity is not a point, but a ring, a spinning loop of infinite curvature. The exact meaning of this structure is still debated, but in the mathematics, it creates something extraordinary, a region of space that may be passable, a hypothetical passage through the center. This ring singularity, in theory, opens up the possibility of a wormhole, a tunnel to another part of spacetime. Whether such a thing could exist in reality is deeply uncertain. The inner structure of a spinning black hole is unstable in most models. Small disturbances can cause it to collapse or fluctuate wildly. But the mathematics, taken at face value, suggests a kind of gateway. Not a doorway in the usual sense, but a pathway built into the curve of space itself. If this were real, it would imply that black holes are not just endpoints, but bridges. That falling into one might not mean destruction, but relocation. There is no evidence that this happens in nature, and most physicists believe the internal structure is more chaotic than these solutions suggest. But still, the ring singularity remains a fascinating clue, a glimpse at what curved space might allow under extreme conditions. It shows how much we still have to learn about the shapes within. There is another kind of black hole permitted by Einstein's equations, one that carries electric charge. These are described by the Reisner-Nordström solution, which adds charge to a non-rotating black hole. Like mass, electric charge affects spacetime. It alters the shape of the curvature and introduces new boundaries. A charged black hole has not one but two horizons, an outer one similar to the usual event horizon and an inner one where the geometry becomes even more extreme. The addition of charge changes the internal structure. Between the two horizons lies a region where time and space behave in even stranger ways. If you were falling in, you would cross the outer horizon first, losing contact with the outside world. But you would not hit the singularity immediately. Instead, you would pass through another horizon, beyond which the curvature becomes stronger still. The path continues inward, toward a singularity similar in many ways to the one in the Schwarzschild case, but now shaped by both gravity and electromagnetism. In practice, it's unlikely that black holes in nature carry much charge. Any significant imbalance would quickly attract opposite charges from the surrounding environment, neutralizing the effect. But as a mathematical possibility, charged black holes are valuable. They show how general relativity accommodates not just mass, but other forms of field and energy. They reveal new structures within the theory, horizons, boundaries, and internal regions that do not exist in the uncharged case. When mass, spin, and charge are all present, we get the most general type of black hole permitted by classical general relativity, the Kerr-Newman black hole. It is spinning, charged, and curved in every direction. Its geometry is the most complex of all, and its interior contains the richest set of possibilities. Like the simpler Kerr solution, it includes a ring singularity. Like the Reisner-Nordström black hole, it includes multiple horizons. It also predicts regions of negative energy and complex paths through spacetime. These solutions are mathematical, perfect, symmetric, and eternal. But nature rarely offers perfect symmetry. Real black holes are formed from collapsing stars, merging giants, and chaotic processes. They are rarely static. They ripple, wobble, and settle. Still, these idealized models give us a map. They tell us what's possible, at least in theory. And in doing so, they stretch our imagination, revealing geometries that go far beyond anything we experience in daily life. At their most abstract, these solutions hint at something extraordinary, that black holes might be portals to other regions of spacetime, that beyond the horizons, the map might continue. Wormholes, white holes, tunnels, these are all allowed, in principle, by the equations. But they come with conditions: perfect symmetry, total stability, exotic matter. So far, we've seen no evidence for any of these in nature. But their mathematical existence challenges our understanding. They remind us that general relativity is not just a theory of gravity, it is a theory of shape. And some shapes are stranger than we've ever seen. Every black hole begins as something else. And most often, that something is a star. A massive, luminous sphere of gas burning with the heat of fusion. For millions or billions of years, the star balances two opposing forces: the inward pull of gravity and the outward pressure from the nuclear reactions at its core. Hydrogen fuses into helium. Energy escapes as light, and that light pushes back against collapse. The result is equilibrium, a delicate, ongoing tension between contraction and expansion. The more massive the star, the more intense this struggle becomes. Gravity pulls harder. Temperatures soar. New layers ignite. Helium becomes carbon. Carbon becomes oxygen. The process builds inward and upward, creating shells of fusion like the layers of an onion. Each new stage yields heavier elements, but the pressure always depends on heat. And that heat comes from fusion. When the reactions continue, the star survives. When they end, the balance breaks. At the end of a massive star's life, iron appears at the center. And that marks a turning point. Iron cannot be fused into heavier elements without consuming energy instead of releasing it. The chain reaction stops. The furnace goes cold. And without pressure from fusion to counteract the immense gravitational force, the core begins to collapse. This collapse happens in a matter of seconds, and it sets the stage for one of the most dramatic transitions in the cosmos. As the core shrinks, the outer layers fall inward. Pressures rise beyond anything seen in ordinary matter. Electrons are crushed into protons, forming neutrons. Neutrinos flood outward. A shock wave rebounds, ripping through the infailing gas. If the conditions are right, this shock wave becomes a supernova, a titanic explosion that can outshine an entire galaxy. The outer layers are cast off into space. But the core, now incredibly dense, remains behind. And what it becomes depends entirely on its mass. If the remnant is small enough, it may stabilize as a white dwarf or a neutron star. These are exotic objects in their own right, supported by quantum pressure, degeneracy effects that arise from the rules of particles at high density. But if the mass is too great, even this exotic pressure cannot hold back gravity. There is a limit, known as the Tolman-Oppenheimer-Volkoff limit, beyond which no known form of matter can resist collapse. When that limit is exceeded, the outcome is inevitable. Gravity overwhelms everything. The core compresses past the neutron star stage, and no known force is strong enough to stop it. The curvature steepens. The surface vanishes, and a black hole is born, not in a violent explosion, but in a final inward slide, as the geometry folds completely in on itself. What remains is not a remnant of matter, but a region of spacetime with no escape. The end of the star becomes the beginning of something new. When the balance inside a massive star breaks, the collapse begins not at the surface, but deep within the core. The innermost region, once hot and stable, gives way to gravity. At first, the contraction is slow, resisted by the quantum pressure of electrons. But as density increases, the electrons are forced into higher and higher energy states until they begin to combine with protons, forming neutrons. This changes the character of the matter itself and removes the final barrier against collapse. The core suddenly becomes opaque to its own light. Heat and pressure build rapidly, but before they can be released, the structure tightens further. At this stage, densities rival those of an atomic nucleus, something like 100 trillion grams in every cubic centimeter. Time slows. The infilling material accelerates. And then, for a brief moment, the inward motion halts. A rebound begins. This rebound is the shock wave that starts the outward blast, the first spark of a supernova. Yet the shock alone is not always enough to drive the explosion. Much of the energy gets absorbed or stalls in the surrounding layers. What saves the process, at least in some models, is the flood of neutrinos. These ghost-like particles, created in huge numbers during the collapse, stream outward with nearly the speed of light. Though they interact only weakly with matter, the density is so high that even a tiny fraction of absorption can reignite the shock wave. When this happens, the outer layers are torn away in a single blinding pulse. The result is a core collapse supernova, a single star undergoing a transformation so violent it can briefly rival the brightness of an entire galaxy. This is where the heavy elements are made: gold, uranium, and everything beyond iron. In that moment, a star gives back its contents to the cosmos. But at its heart, something denser remains. And whether it becomes a neutron star or a black hole depends not on the explosion, but on what's left behind. There are thresholds determined by mass that govern this outcome. If the core is less than about 2 to 3 times the mass of the Sun, it can stabilize as a neutron star, an object so dense that a teaspoon would weigh more than a mountain. It holds itself up not with fusion, but with neutron degeneracy pressure, a quantum resistance to further compression. These are stable, long-lived remnants, spinning and glowing, sometimes pulsing like cosmic beacons across the sky. But if the mass exceeds the limit, degeneracy pressure fails. Gravity crosses a point of no return. And instead of a solid remnant, the core continues to collapse, falling inward through its own horizon. No light escapes. No surface remains. The event horizon forms around it. And from that point on, the black hole exists, not as an object in space, but as a region of space where the past ends in silence. The formation is complete. The star is gone, but its gravity lives on. Neutron stars are among the strangest stable objects in the universe. They form when the collapsing core of a massive star stops just short of becoming a black hole. At this point, the matter is compressed so tightly that the protons and electrons have merged into neutrons. These neutrons form a superdense fluid, no longer composed of atoms, but of nuclear matter packed into a state beyond anything seen in ordinary physics. It is not solid, not gaseous, not even plasma. It is something else, structured by quantum rules alone. The force that holds this object up is called degeneracy pressure, a quantum mechanical effect that emerges from the Pauli exclusion principle. It states that no two identical fermions, particles like electrons or neutrons, can occupy the same quantum state. As the core compresses, neutrons are squeezed into fewer and fewer possible states. Eventually, the resistance from this rule becomes strong enough to halt further collapse. The result is a star only about 10 to 15 kilometers across, but more massive than the Sun. On the surface of a neutron star, gravity is hundreds of billions of times stronger than Earth's. The crust is only a few centimeters thick. Beneath it lies a sea of superfluid neutrons, spinning, flexing, and vibrating with strange rhythms. Some neutron stars spin hundreds of times per second. Others emit beams of radiation, sweeping across the sky like cosmic lighthouses. These are the pulsars. They are precise, stable, and deeply mysterious. But they are not invulnerable. If enough matter is added, their structure will collapse. The limit beyond which a neutron star can no longer support itself is called the Tolman-Oppenheimer-Volkoff limit, or TOV limit for short. It's the neutron star equivalent of the Chandrasekhar limit for white dwarfs. While the exact value depends on details of nuclear physics that are still being studied, it's generally estimated to be around 2 to 3 solar masses. Beyond this point, neutron degeneracy pressure is no longer enough. Gravity takes over, and no known state of matter can stop the collapse. The TOV limit represents the dividing line between the visible and the hidden. Below it, we get neutron stars, observable, compact, sometimes even predictable. Above it, we enter the domain of black holes. Once crossed, the structure cannot stabilize. No internal force can resist. The collapse continues, not to a new kind of star, but to a new kind of region, one where the rules of motion and space no longer offer any escape. It is the threshold of invisibility. This limit also hints at the mystery of dense matter. We do not fully understand what happens inside neutron stars. Some theories suggest that the core may dissolve into quark matter, an even denser state where individual neutrons break apart into their constituent particles. Others speculate about hyperons, meson condensates, or strange matter. Each of these could, in principle, raise or lower the TOV limit. But until we can observe these interiors more directly, the black hole remains the final answer when mass crosses the line. When the collapsing core of a massive star passes the TOV limit, no known force can stop it. The pressure from neutrons, the tension from nuclear forces, even the resistance of quark matter, none are enough. Gravity curves space so sharply that no stable configuration remains. The matter continues to fall inward, accelerating as it goes. Time, from the outside, slows down near the edge. But for the matter itself, the plunge continues, swiftly, deeply, unstoppably. The collapse doesn't explode. It doesn't freeze. It passes a point of no return and keeps going. From the outside, an event horizon forms, a spherical boundary where the escape velocity reaches the speed of light. Inside this boundary, the space continues to fold, guiding all paths toward the singularity. The core no longer exists as matter in space. It has become part of a new geometry, a region, not a thing, a shape where light cannot escape. This moment marks the true birth of a black hole, not as a leftover object, but as a transformation of the space-time itself. The gravitational field persists. The mass remains. But there is no longer a surface, no longer a place to point to and say, "Here is the star." The black hole is not made of matter anymore. It is made of the space that once surrounded it, reconfigured, sealed, and redefined. The star is gone, but its presence endures in the warping it left behind. Black holes don't remain fixed in size. They can grow. And one of the primary ways they grow is by feeding. When gas, dust, or even stars drift too close, they may fall in. Not all at once, but gradually, spiraling inward through a structure called an accretion disk. This disk is flat, spinning, and often extremely hot. Friction between the layers causes the matter to heat up and radiate energy, sometimes enough to outshine entire galaxies. The process is not clean. As matter falls toward the black hole, it loses angular momentum and energy. Magnetic fields twist. Plasma flares. Turbulence stirs the disk into a glowing storm. The closer the material gets to the event horizon, the faster it moves. Some of it falls in. Some escapes in jets, blasting out along the poles at nearly the speed of light. These jets are not coming from inside the black hole, but from the outer regions of the disk, launched by magnetic forces and rotation. Despite the violence, this process is efficient. A black hole can convert a significant portion of the infilling matter's mass into energy before swallowing it. This makes accretion one of the brightest engines in the universe. In some cases, black holes power quasars, supermassive beacons that shine across cosmic distances. These feeding processes can last millions of years, transforming quiet galaxies into active ones. The black hole remains hidden, but the feast leaves a blazing signature behind. Some of the clearest evidence for black holes comes not from solitary giants, but from pairs, binary systems where a black hole orbits a companion star. In these systems, matter from the star can spill toward the black hole, pulled off by tidal forces and channeled into an accretion disk. The infilling gas heats up, radiating intense energy, especially in the form of X-rays. These high-energy emissions can be detected from Earth, revealing the presence of something massive, compact, and invisible. Unlike ordinary stars, these compact objects don't emit their own light, but their fingerprints are clear. The way they move, the way they bend light, and the energy released from the surrounding disk all point toward their nature. Some of the earliest black hole candidates, like Cygnus X1, were discovered this way. A visible star, orbiting something dark, massive, and small enough to be a black hole. These systems offer a unique window into black hole growth in action. When two black holes orbit one another, the system becomes even more intriguing. Over time, they spiral closer together, radiating energy in the form of gravitational waves, ripples in space-time itself. These waves carry away momentum, causing the orbit to shrink. Eventually, the black holes merge in a violent coalescence, sending out a final, powerful wave that spreads across the universe. These events are rare, but they are now directly observable. The first detection of gravitational waves came in 2015 from the merger of two black holes more than 1 billion light-years away. The signal lasted less than a second, but carried the mass of several suns. It confirmed a prediction of general relativity made 100 years earlier and opened a new kind of astronomy, not with light, but with the stretching and squeezing of space itself. Each merger we detect tells us about mass, spin, and distance, about how black holes meet and how they grow. These gravitational waves are not just echoes of violence. They are records of geometry in motion. They tell us that black holes are not silent after all. They sing in a language of curvature and rhythm when they collide. The final object left behind is larger than either black hole alone, but not as massive as their sum. Some of the energy has been radiated away in waves, leaving behind a new, heavier, spinning black hole. These mergers contribute to the cosmic population of black holes. They help seed larger structures. Over billions of years, through collision and growth, black holes scale up from the remnants of stars to something much more immense. They become the gravitational hearts of galaxies, not through sudden creation, but through a long process of accumulation. They grow not just by swallowing stars, but by merging with each other, knitting together the deep geometry of space. Between the stellar mass black holes born from dying stars and the giants at galactic centers lies a mysterious category: intermediate mass black holes. These are objects with masses ranging from a few hundred to a few 100,000 times the mass of our Sun. For decades, their existence was uncertain. Too heavy to form from a single star, too light to match the giants we see in galaxies, they sat in a kind of observational limbo, a missing population between the known extremes. Hints of their presence began to emerge in dense star clusters. In some of these ancient spheres, the motion of stars suggests the influence of a hidden mass, compact, dark, and larger than any single star. X-ray emissions from ultraluminous sources have also pointed to accretion by something heavier than a stellar black hole, but not large enough to be considered supermassive. These may be the long-sought intermediates, slowly revealing themselves in the quiet corners of the cosmos. How they form is still an open question. One possibility is runaway collisions in young star clusters, where massive stars merge before they explode. Another path may involve the gradual buildup of mass through accretion and mergers, bridging the gap between stellar and galactic scales. Whatever the route, intermediate mass black holes may be the seeds, the precursors to the giants we now see anchoring galaxies across the sky. Supermassive black holes are the largest known. They reside at the centers of galaxies, including our own Milky Way. These giants range from millions to tens of billions of solar masses. And yet, despite their enormity, their gravity can be surprisingly gentle at the horizon. A person falling into one might not even notice crossing the edge. The curve of space is gradual, stretched over a vast region. These are not dense in the traditional sense. They are massive, yes, but spread across a wide and quiet sphere. How these monsters formed remains one of the great puzzles in astrophysics. Some may have grown slowly over billions of years, fed by gas, dust, and merging stars. Others may have formed rapidly in the early universe from the direct collapse of primordial clouds. Observations of quasars, brilliant beacons from ancient times, suggest that some supermassive black holes were already in place less than 1 billion years after the Big Bang. The speed of their growth challenges many models and invites new ones. What is clear is that supermassive black holes are not passive occupants of galactic centers. They shape their environments. Their gravitational pull governs the motion of stars. Their radiation affects the flow of gas. They regulate star formation and influence the structure of the galaxy itself. And in some cases, they launch jets that span hundreds of thousands of light years. These are not just endpoints, they are engines. And their role in cosmic evolution is profound. Around many black holes, especially the massive ones, swirls a luminous storm of matter called an accretion disk. This disk forms as gas and dust spiral inward, drawn by gravity but slowed by friction and angular momentum. As particles rub against each other, they heat up. Temperatures soar into the millions of degrees. The inner regions of the disk shine with X-rays and ultraviolet light. Though the black hole itself remains invisible, the disk can blaze with astonishing brilliance. These disks are not just bright, they are dynamic. They twist and ripple. Magnetic fields arc and reconnect. Turbulence creates eddies and waves. And sometimes, something even more extraordinary happens. The black hole launches jets. These narrow beams of particles and radiation shoot out from the poles of the disk, traveling at nearly the speed of light. They extend far beyond the galaxy, piercing intergalactic space with focused streams of energy. The exact mechanism behind these jets is still under study, but magnetic fields likely play a central role. As the spinning disk twists the fields, it creates a kind of coil that channels energy outward. The rotation of the black hole itself may also contribute, extracting spin and converting it into kinetic energy. Whatever the process, the result is among the most powerful events in the universe. A silent object emitting a roar of light and motion across millions of light years. These effects are not confined to the black hole's immediate surroundings. The energy released from accretion and jets can reshape entire galaxies. It can heat gas, suppress star formation, and carve out cavities in the interstellar medium. This is known as feedback, and it plays a crucial role in regulating the growth of galaxies. Without it, galaxies might grow too fast or form stars too freely. The black hole, tiny compared to the galaxy, acts as a governor on its evolution. This feedback operates on vast scales. A single supermassive black hole, through its radiation and jets, can influence the behavior of stars hundreds of thousands of light years away. It can limit cooling, disperse clouds, and drive winds that sweep through the galaxy's halo. Observations of elliptical galaxies often reveal signs of this influence: giant bubbles, shock fronts, and filamentary structures shaped by past outbursts. These are not random accidents. They are signs of a central engine at work. In this way, black holes are not merely endpoints. They are shapers of structure. Their influence begins small, in the twisting of a disk or the launch of a jet, and extends outward into the architecture of space itself. They grow by feeding, but in turn, they guide the flow of matter and energy. From the heart of a galaxy, silent and hidden, they sculpt the form of the cosmos on scales both intimate and immense. The edge of a black hole is not marked by matter or structure. It is marked by time. From a distance, objects that fall toward a black hole seem to slow as they approach the event horizon. Their motion becomes sluggish, their signals stretch. This is not a trick of vision, it's a fundamental effect of curved spacetime. Gravity alters the flow of time, and near the horizon, that flow stretches toward infinity. The closer you get, the more time slows, at least, as seen from far away. This slowing is not experienced by the falling object. Its own time continues smoothly. Seconds tick by. Instruments read normally. But to a distant observer, those seconds are spread out over hours, years, centuries. The object never seems to cross the horizon at all. It hovers, frozen in descent, its image fading but never gone. In reality, it does fall, but the light it emits becomes so stretched, so delayed, that the final moment never quite arrives. This strange behavior is an expression of Einstein's equivalence between gravity and time. In strong gravitational fields, clocks tick more slowly. Near the surface of Earth, this effect is tiny, a few billionths of a second per year. But near a black hole, it becomes dramatic. The difference in time between the horizon and infinity can be essentially infinite. To look down into that well is to look into the deep future. To fall in is to leave one timeline and enter another. The slowing of time is tied to a second effect, gravitational redshift. As light climbs out of the gravitational field, it loses energy. But light cannot slow down. So instead, its wavelength stretches, it shifts toward the red end of the spectrum. The stronger the gravity, the greater the shift. Near the event horizon, the effect becomes extreme. Even visible light is redshifted into infrared, then microwave, then radio. Eventually, it becomes undetectable altogether. This redshift is not caused by motion, as in the Doppler effect, but by the geometry of space itself. The light has not changed, it is simply climbing through a warped landscape, and that climb leaves it stretched. For a falling object, this means that any signal it emits grows fainter, longer, and more delayed. To a distant observer, it appears to vanish, not by stopping, but by thinning out across time. The final moments are smeared across the ages. These two effects, time dilation and redshift, define the edge of a black hole. They tell us where the visible world ends. Not with a wall, not with a flame, but with a silence that deepens by degrees. The event horizon is not a surface that blocks. It is a boundary where light becomes endlessly tired and time becomes endlessly slow. Nothing dramatic happens at the threshold, but once crossed, the return path vanishes. The light weakens, the clock slows, and the view from outside fades into nothing. From a distance, the fall into a black hole looks infinite. The object seems to hover forever just above the event horizon, its image dimming and reddening until it disappears from view. But from the point of view of the falling object, that's not what happens at all. It moves forward in time like always. The horizon approaches, is crossed, and recedes behind it. There's no pause, no freeze, no moment of stalling. Just motion, downward, inward, smooth. These two perspectives aren't in conflict. They're both correct, within their own frames of reference. This is one of the deepest insights of general relativity, that different observers can describe the same event in very different ways, and both can be right. To the outside world, the fall stretches into eternity. To the infilling traveler, it's finite. The contradiction disappears when we understand that time itself is not absolute. It bends with gravity, and at the edge of a black hole, it bends completely. To resolve this difference, Physicists use two kinds of time: coordinate time and proper time. Coordinate time is measured by a distant observer, far from the black hole, where space-time is flat and clocks run uniformly. It's the time marked by telescopes and detectors, satellites and sensors. Proper time is what a clock experiences along its own path. It's local, personal, unshared. It's the time on your wristwatch, ticking as you move through the world. These two measures agree when gravity is weak, but near a black hole, they diverge. Coordinate time slows down near the horizon, reaching infinity at the threshold. But proper time remains finite. A person falling in might experience the entire descent in just a few seconds or minutes of proper time, while to the outside world, that same fall appears to take forever. The falling object doesn't know it's stretching out. Its own clock tells a consistent story. This distinction is more than theoretical. It's essential to understanding how black holes interact with the rest of the universe. What looks like a slow freeze from one view is a rapid plunge from another. Signals, light, and energy behave differently depending on which perspective you adopt. It's why astrophysical black holes, though hidden, can still influence galaxies. The matter that falls in appears to linger near the edge, glowing, flaring, fading. And yet, for that matter itself, the journey is already over. At the heart of all this is a subtle truth. Space-time is not a stage. It is an actor. It shapes what can happen and how it appears. The fall into a black hole is not just a motion through space. It is a reshaping of time itself. One observer sees delay. The other feels descent. Between them lies the event horizon, a boundary that doesn't stop time, but bends it so far that it no longer connects the two. For the object falling inward, the event horizon is not a wall. It is not sharp or sudden. It has no surface, no shock. It cannot be seen or felt. There are no signs, no lights, no markers. And yet, once crossed, it changes everything. From the outside, the object never quite reaches this threshold. But from the inside, the crossing happens smoothly, unnoticed at first, irreversible forever. The horizon is a boundary in the geometry of causality. After this point, all possible paths point inward. To cross the event horizon is to enter a region where space and time have traded roles. Outside the black hole, you can move through space freely, and time carries you forward. Inside, it's the opposite. Space becomes a direction you cannot avoid. You move inward not by choice, but because every possible motion leads that way. The center lies ahead in every frame. Even if you try to resist, to turn around, there is no direction left to escape into. The moment of crossing can be quiet. A spacecraft, falling freely, might feel nothing. No tidal force, no sudden pull, especially if the black hole is supermassive and the curvature is gentle at the edge. Yet the crossing is absolute. No signal can leave. No course can be reversed. The rest of the universe becomes a thing you can remember, but never reach again. The black hole is not sucking you in. It's simply that the path ahead and every path leads inward now. The horizon is where light becomes trapped. Photons emitted outward from just inside the edge still move at light speed, but they are carried inward by the shape of space-time. Like a swimmer in a current stronger than any stroke, they cannot make headway. From the outside, light emitted from the edge is stretched infinitely, redshifted to invisibility. From the inside, light still exists, but it cannot return. The horizon is a one-way surface, not for motion, but for information. This makes the horizon more than a location. It is a causal boundary, a surface that divides events into two realms, those that can affect the outside universe and those that can't. It is not a solid thing, but a limit in what is possible. From outside, we can see things fall toward it, but we can never see anything cross. From inside, you can cross it without noticing, but you cannot cross back. The asymmetry is not physical, but geometric. To truly understand the horizon, we must let go of the idea that space is a container, or that motion can always be reversed. The event horizon is the edge of return. Once past it, all timelines lead inward. Not because anything pushes you, but because the structure of reality itself has shifted. The horizon is not a trap. It is a turning of the map. And beyond it lies a region where even the meaning of direction begins to dissolve. In relativity, the concept of a light cone helps us understand what's possible. At every point in spacetime, the light cone shows the directions light can travel from that point, forward in time, outward in space. Anything inside the cone is reachable by signals or motion. Anything outside lies beyond influence. As you move through curved space, the light cone tilts, bends, and shifts, responding to gravity. Near a black hole, it begins to tip inward. At the event horizon, it tips completely. At the exact location of the horizon, the future light cone no longer includes directions that point away from the black hole. All the future paths, even for light, now lead inward. This doesn't mean light slows down. It's still traveling at light speed. But the shape of the space it travels through has changed. The directions it could have taken no longer exist. Every beam bends inward, carried by the curve of spacetime toward the singularity. This shift marks a fundamental change. The tipping of the light cone isn't just a geometric curiosity. It means the very structure of cause and effect has turned. No future exists outside the black hole anymore, not for anything that crosses the horizon. All timelines converge inward. The center is not a place you move toward. It is a moment that lies in your future, unavoidable, certain, and silent. Once the light cone has turned, the rest of the universe lies only in memory. Once matter falls into a black hole, its individual features seem to vanish. The atoms, molecules, structures, all disappear behind the event horizon. What remains from the outside can be described by just three quantities: mass, spin, and charge. These are the only measurable features a black hole appears to preserve. All other details, the composition of the star, the shapes of the collapsing layers, the history of its motion, are lost. This is the essence of the no-hair theorem. The name is informal, but the idea is precise. Black holes have no hair, no surface features, no individuality. They're defined by a few global parameters, and otherwise, they are smooth. The matter that fell in may have been complex, but the black hole it formed is not. Two black holes with the same mass, spin, and charge are indistinguishable, no matter how differently they were born. From the outside, they are identical. This raises deep questions. If a complex system collapses into a black hole and all its detail is lost behind the horizon, where does that information go? Is it destroyed? Is it hidden? Or is it encoded somehow in the geometry of spacetime? The no-hair theorem says that black holes forget, but quantum mechanics suggests that information cannot be destroyed. The tension between these two principles leads us to one of the great mysteries of modern physics. The information paradox begins with a contradiction between two of physics' deepest principles. On one side is general relativity, which tells us that once matter falls into a black hole, its fine details are lost. Only mass, charge, and spin remain. Everything else disappears behind the event horizon. On the other side is quantum mechanics, which insists that information is never destroyed. Even if particles scatter, combine, or transform, the total information about their state must, in principle, be preserved. This paradox becomes acute when we consider black hole evaporation. If a black hole truly forgets what formed it, and then slowly vanishes through some natural process, the information it once contained would seem to vanish as well. This would violate the laws of quantum theory, not just a minor inconsistency, but a fundamental breakdown. And so physicists began to ask, is the black hole really forgetting? Or is the information stored in some way we haven't yet understood? The question remained unresolved for decades, until a radical idea emerged in the 1970s. Stephen Hawking showed that black holes are not perfectly black. Through the quantum jitter of empty space, black holes can emit radiation. This phenomenon, now called Hawking radiation, revealed that black holes have a temperature, and therefore they can evaporate. Slowly, over unimaginable timescales, they lose mass by releasing this faint glow of particles. Hawking's calculation was built on quantum field theory in curved spacetime. Near the event horizon, virtual particle pairs constantly appear and annihilate. Occasionally, one falls into the black hole, while the other escapes. The escaping particle becomes real, carrying away energy. Over time, this process reduces the black hole's mass. Eventually, it could vanish entirely. But if the radiation carries no information, if it is purely thermal, then the information paradox only deepens. This radiation does not emerge from inside the black hole. It originates near the horizon, shaped by the quantum properties of empty space itself. It is faint, cold, and nearly impossible to detect for stellar black holes. But its implications are profound. If black holes can evaporate, they are not eternal. If they emit radiation, they must have entropy. And if they disappear, the question becomes urgent. What happens to everything they swallowed? Hawking originally argued that the information was lost, that black hole evaporation destroyed it forever. But many physicists disagreed. Over the years, new ideas emerged. Some proposed that the information is encoded subtly in the radiation. Others suggested that the horizon might store a holographic imprint of everything that falls in. Still others speculated that black holes don't quite destroy information, but that our understanding of space and time is too limited to see where it goes. To make sense of information in black hole evaporation, physicist Don Page proposed a simple idea. If black holes emit Hawking radiation, and if that radiation carries no information, then the entropy of the radiation should increase steadily as the black hole shrinks. But if the information is somehow preserved and released over time, the curve of entropy must bend. It should rise at first, then fall, resembling a hill. This became known as the Page curve. In the early stages of evaporation, the outgoing radiation appears thermal, random, structureless, and uninformative. But if unitarity holds, if quantum information is conserved, then this cannot continue forever. After a certain point, known as the Page time, the radiation must begin to carry information about the black hole's interior. Entropy peaks, then decreases, ending at zero when the black hole fully evaporates. The information, once hidden, must return in the glow. This presents a challenge to Hawking's original calculation, which predicted no such return. But recent advances, particularly from string theory, quantum information, and holography, suggest that the Page curve may be correct. Techniques borrowed from entanglement entropy have revealed how quantum gravity might encode information on surfaces, not volumes. These hints point to a deeper unity between space, time, and information, one that could reconcile black hole evaporation with the laws of quantum theory. But to know for sure, we must understand the black hole's center, the singularity. In classical general relativity, the singularity is a point of infinite curvature, where density and gravity become undefined. It is not just an extreme location, it is a place where the theory itself breaks down. Equations fail, predictions vanish, and yet, the singularity lies in the future of every infilling object. If we want a complete picture, we must go there too. This is where quantum gravity becomes essential. General relativity cannot handle singularities on its own. The theory treats spacetime as smooth, continuous, and geometric. But quantum mechanics says the world is made of discrete, fluctuating units. Somewhere near the Planck scale, where distances are measured in trillionths of a centimeter, these two pictures must meet. And in that meeting, the singularity may dissolve. Many candidate theories of quantum gravity exist: string theory, loop quantum gravity, causal sets, emergent spacetime. Each offers different tools for smoothing out the singularity. Some suggest that spacetime is not fundamental at all, that it arises from a deeper quantum structure. Others propose that information is stored in entanglement itself. Still others imagine that the core of a black hole is not a singularity, but a bounce, a point from which a new universe might begin. In trying to understand the true nature of black holes, physicists have been led into stranger and stranger territory, ideas that seem to border on science fiction, yet arise naturally from the equations. One of these is the concept of wormholes, tunnels through spacetime, possibly connecting two black holes or two distant regions of the universe. If such structures exist, they might offer a path through a black hole rather than a dead end. But most solutions that allow for traversable wormholes require exotic matter or unstable conditions. For now, there remain mathematical possibilities. Another idea, almost the reverse of a black hole, is the white hole. Where black holes allow nothing to escape, white holes allow nothing to enter. They are time-reversed versions of collapse, explosions instead of implosions. In theory, information that enters a black hole could emerge from a white hole somewhere else. Some speculative models suggest that black hole evaporation might transition into a white hole phase, releasing stored information in a final burst. But no white holes have ever been observed. And then, there are firewalls. Proposed as a resolution to the information paradox, the firewall hypothesis suggests that the event horizon might not be smooth and empty, as general relativity predicts, but violently energetic. If information is encoded in the Hawking radiation, then something must break, either unitarity, the equivalence principle, or the idea that nothing special happens at the horizon. A firewall would be a wall of high-energy particles that burns anything crossing it. But this idea remains deeply controversial. All of these models, wormholes, white holes, firewalls, are attempts to answer one question: how does information escape? If it doesn't escape, then quantum theory must give way. If it does, then our understanding of spacetime must change. And increasingly, physicists are realizing that the answer may lie not in matter, but in entanglement, the invisible threads that bind quantum systems together. Entanglement is not just a feature of particles, it may be the scaffolding of space-time itself. Some researchers now believe that the smooth geometry of space emerges from patterns of entanglement, like a hologram formed from correlations. In this view, the interior of a black hole is not a hidden place, but a construction of quantum relationships. And when information escapes in radiation, it does so through the shifting pattern of those connections. This idea leads to a startling possibility that space and time are not fundamental ingredients of reality, but side effects of quantum information. If so, then the edge of a black hole is not the end of understanding, it's the beginning of something deeper. A place where the known rules give way, not to chaos, but to structure we haven't yet fully uncovered. A place where physics begins to whisper the language of its own origin. So now, here we are. The journey has taken us through warping gravity, collapsing stars, and invisible thresholds. We've hovered at the edges of light and slipped softly inward, past horizons drawn not in matter, but in time. And perhaps, in the quiet space where science dissolves into silence, the mind begins to let go. There's no need to remember the details now. The equations can wait. The paradoxes can rest. What remains is a shape in thought, a sense of something vast and curved, calm and inevitable. A presence not made of matter, but of gravity alone. A place where time folds inward, where even light must bow to the shape of the dark. Out there, among the drifting galaxies, black holes wait in stillness. Some are ancient giants, seated in the centers of galaxies like sleeping gods. Others are small and hidden, pulsing faintly in the shadows between stars. They do not seek. They do not chase. They simply are, their presence defined not by what they hold, but by what they will not let go. And maybe, in some way, the quiet of a black hole is not so different from the quiet of a sleeping mind. Both slip beneath the surface. Both let the world fall away. Both surrender to something slower, deeper, ungraspable. Not an end, but a region from which no thought must return. You don't need to follow anymore. If you've drifted, that's just right. If your thoughts have wandered, they're welcome to stay wherever they are. If your eyes have closed, let them rest a little longer. And if you happen to still be awake, listening softly at the edge of sleep, we'd love to hear your thoughts. Did anything in this video surprise you? Did you learn something new? Feel free to let us know down in the comments. And if you'd like more quiet journeys like this, you're always welcome to subscribe. Because the story continues. It always does. In every atom, in every orbit, in every quiet curve of space. We may never see the centers. We may never know the edges. But we're part of the shape, all the same. And so, under the quiet stars, the story continues. I hope you sleep well and dream softly. Good night.